Good morning and hello. This is Mrs. Gupta. Hope everyone is safe and healthy. This video is a part of a 2 week lesson on thermochemistry. It is the first lesson for marking period 4, week of April 20th, 26th. Let me introduce you to some key terms and equations before we start. Heat, lowercase q, enthalpy, delta H, remember delta is a change of the total, thermochemistry, endothermic processes, exothermic processes, calorie with the lowercase cal, joule, uppercase J, heat capacity, joules per degree Celsius, specific heat, joules per gram degree Celsius, and specific heat equation, which is Q delta H, which is equal to mCp delta T. The objective for this lesson are twofold. The first one is the conservation of energy, where energy cannot be created or destroyed, it can only be transferred. And the another one is the energy cannot be created or destroyed, but it can be transported from one place to the another and between the systems. The agenda is that you will be watching the thermodynamics YouTube video created by me, which is the title Thermodynamics Overview, First Law of Thermodynamics. It will cover specific heat and the types of heat transfer. Then you will be answering the questions 17.1 thermochemistry practice problems, the Google form, and review the feedback, and also answer 17.1 exit card. So basically, two things are due by Sunday midnight, and that is 17.1 practice problem. Those are 10 points and will grow in your classwork category, and 17.1 exit card, 5 points, which will go in your all task category. So let's discuss some real life scenarios. The cup of coffee you order before class loses heat the second it's poured in the cup. It takes a bit of time for that coffee to cool down enough for us to drink. So suppose I'm a coffee person and I order coffee from Starbucks on my way to school. I don't start drinking it as soon as I order and I get it. It is ready to drink in the middle of the first period. In contrast, French fries from a drive-through are cold and soggy before you get home. So French fries are good as soon as you get out of the fryer. While coffee is good after a while, otherwise you're going to burn your tongue, which I've done several times. Have you ever wondered why some things cool faster than the others? Why coffee is taking longer time and the French fries are cooling fast? So let's go over some definitions before we do the first law of thermodynamics. Energy, it exists as work or heat. Work is basically the force required to move an object the distance. Force like gravity, or there are different kinds of forces which are going to like get introduced in physics. So let's concentrate on the heat for our chemistry purpose. Energy is represented by or shown by the symbol E, uppercase E, and the units are joules, uppercase J. Calorie is also a unit for energy, but SI, the International System of Unit, is joule, uppercase J. 1 calorie is 4.18 joules. Heat, on the other hand, is the energy that transfers from one object to another due to the temperature difference. It is shown by the symbol Q. And temperature is the average kinetic energy of the particles in a substance, units being degrees Celsius, Kelvin, and Fahrenheit. If you really remember, Celsius is the Kelvin that we use in our science class and in the labs. Fahrenheit is the one that we use in our day-to-day lives. So if you're going back to the temperature, if you remember, temperature is the average Ke of the particles. So look at these two situations. Here the temperature is 20 degrees Celsius and the particles are moving slowly. The vector diagram is showing you the motion of the particles, which is a small arrow, versus 60 degrees Celsius where the temperature is high and the particles are moving fast and the kinetic energy is high. So when the temperature is low, the particles are moving slowly and the kinetic energy is low. But as the temperature goes up, the particle motion goes up and the kinetic energy also goes up, as you can see in the second situation. So what is thermochemistry? So thermochemistry is the study of energy changes that occur during the chemical reactions or the phase changes. And that's what we're going to concentrate today. Enthalpy, on the other hand, is the heat content in a system at a constant pressure because it changes with the pressure. And for our purposes, heat is a change in enthalpy. So Q is equal to delta H. So I will introduce you to these two situations and then I will go back to our FET that we did last time. So look at this red block, which is at a higher temperature. You can see the thermometer. The particles are moving very fast. And look at another block, which is the blue one, where the temperatures are moving slowly. The temperature is low. The kinetic energy is low. Now, when these two blocks they come together, then what happens is heat flows from the red block to the blue one, the higher temperature to the lower temperature, higher heat to the lower heat, till the temperature in both the blocks becomes the same. If you really remember the FET that we did last time, that iron block was heated and dropped to the cold water, and the iron lost the heat, and the water gained the heat. Or you can also think about my cold coffee with a lot of ice cubes. So ice, lot tons and tons of ice cube in that glass. So what is happening is my coffee is losing energy to the ice till both the systems, ice and the energy, they are in equilibrium and the same amount of temperature or the heat. So let's talk about the direction of the flow of the heat. Heat always flows from a warmer object to the colder object. So look at the object 1 is a higher temperature and object 2 which is at the lower temperature. So T1 is more than the T2. Now heat will start flowing from the T1 to the T2 till the T1 and the T2 are equal and both the objects are at the same temperature. And when this happens, when both the objects are the same temperature, the rate of transfer is the same between the two objects, and we say the system has reached thermodynamics. Everything has heat, and everything has an enthalpy, and everything is moving unless and until, and everything has kinetic energy unless and until it reaches absolute zero, which is a 0 K, negative 273 degrees Celsius, the coldest temperature known, where the motion particle absolutely ceases. So that leads us to the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed, but it can be transformed from one form to the other. Remember the fact that we did from mechanical to the heat, heat to the light, and back to the mechanical. So, change or the total energy in the universe will be the change in the system energy plus the enthalpy of the surroundings, and the difference in the two will always be equal to zero. So if you really look at the guy transferring the hot packet, it can go, he can continuously keep on transferring, but energy cannot be created or destroyed. The heat can be transferred from one form to another. So matter has energy and heat is constantly being transferred in the universe from hot to the cold, hot to the cold, hot to the cold over and over again till the system reaches equilibrium. For that thing, we should all must understand what is a system and what is a surrounding. A system is a part of the universe that is being studied, that is very important for us. Here, the system can be the chemical reaction that is going on in this Erlenmeyer flask. This system can be open or closed. In the open system, matter can move freely between the system. For example, if when I was lighting the Bunsen burner, the methane combining with the oxygen gave you a lot of energy and carbon dioxide and water. As the system was open, both the matter, the water, and the carbon dioxide and energy moved between the systems. It can be a closed system where the only matter can move in and out sorry, but only matter cannot move in and out, only energy can move. So if I put like this chemical reaction and I completely seal the system and all the matter will be within the system only. The surroundings are everything else in the immediate vicinity of the system. So in this case, the surroundings is my air around the block. Let me go back to the system and give you more examples to understand what a system and a surrounding is. For example, when I'm making this video, it was a cold afternoon and I'm sitting next to my fireplace. So me, my body is the system and the fireplace is the surrounding, and the heat is traveling from the fireplace to my body, making me feel warm. Now, after the system, after this making this video, I will try to go and work out. What will happen when I work out? I will sweat, and the heat will now leave my body to the air, that is the surroundings of the body. Now let's go and review the endothermic and the exothermic processes that we have studied in the graphs before too. So endothermic process is a system that gains heat and the surroundings cool down. So look at this flask, which is my system, and the outside is my atmosphere or the air, which is the surrounding. So heat is flowing from the surrounding to the system. The heat system is gaining the heat. So what is happening? The surroundings are getting cooled down as they are losing heat, and system is gaining heat, so it is getting warmer. So system is absorbing heat from the surroundings, and surroundings are losing heat. Heat or slash energy is written on the reactant side of the chemical equation, and system has a positive Q or delta H is a positive value when the system is endothermic. But plus Q or delta H shows the system is endothermic. So let me review this again, as it is a very important concept. In the endothermic process, heat travels from the surroundings to the system, surroundings here being air, system being the content in this flask. Surroundings are getting colder and the system is getting hotter. Surroundings are losing heat and system is gaining heat. It is always shown by a positive Q or delta H and always written on the reactant side, that is the left side of a chemical equation. If you really look at the graph that we have already studied, let me review with you. So this graph shows an endothermic reaction where the products are having higher energy than the reactants because the products have gained heat and the products have gained heat, that is the system has gained heat. And delta H will be a positive value as the product is more than the reactant. Delta H is HP minus HR, the heat of the products minus heat of the reactants. So let me discuss this exothermic and the endothermic process in the two most common reactions that we see in nature, the photosynthesis and respiration. So in photosynthesis, carbon dioxide is reacting with the water and energy is getting absorbed from the sun, giving you the glucose molecule C6H12O6 and oxygen. Now, the energy has been written in the left hand side with the reactants and is an endothermic process. Now, this photosynthesis, the reverse process, is the respiration, where the energy that is stored in the glucose is broken down and is released and is written with the product, and this is being the exothermic process. So, photosynthesis being endothermic, energy being written with the reactant, and respiration being exothermic, energy written on with the products. In this case, as it is endothermic, Q or delta H will be a positive value, and Q and delta H in the respiration being exothermic will be a negative value. Here you can see that endothermic and exothermic. So in exothermic, the system loses heat, the surroundings become warmer. So here, this is the system and the surroundings of the air. Heat is flowing from the system to the surroundings. System is releasing heat to the surroundings, as you can see that. Heat energy written on the product side of the chemical equation, and system has a negative Q and delta H is also negative. Delta negative Q and negative delta H is an exothermic process. So again, okay, let's look at the graph, which we've already done before we were quarantined, that the products have a lower energy as compared to the reactants, and delta H will be a negative value as delta H is a HP minus HR, and HP is lower than the HR. So let's talk about the specific heat. Specific heat is the amount of heat it takes to raise the temperature of 1 gram of substance by 1 degree Celsius. Let's review the substance. Here I'm talking about the pure substance, which can be an element or a compound, uniform composition. Um, Element can be me like silver, Ag, anything from the periodic table, and the compound, most common compound that we do is the water, H2O. It cannot be your Chex Mix, it cannot be your French fries, it cannot be your iced coffee, or it cannot be your sand. Specific heat is shown by the symbol Cp. Do not confuse it with the Celsius because it has a lower P. P stands here for pressure as the specific heat changes with the pressure. For our references, we will consider this pressure as constant 1 atm, 1 atmosphere value. The units of specific heat are joules per gram degree Celsius, and it is constant for a given substance. So here, if you really look at it, I'm going to go and discuss with you the specific heat of different substances. Specific heat can be calculated by this equation, the yellow one that you see here. C is equal to Q over M delta T, heat over mass, which is in grams, times the change in temperature in degrees Celsius. This equation, these calculations we are going to do in next week. And so get ready with your calculators. Here we'll study more about the concept. So different substances have a different value of the specific heat. So if you can see here, the water has a very high specific heat, 4.18 joules per gram degree Celsius, and mercury, the metal, the liquid metal, has 0.14, very low specific heat as compared to the water. Why is that so? Because different substances require different amount of heat to raise the temperature by 1 degree Celsius or 1 gram. So that means water requires more heat to raise the temperature of 1 gram by 1 degree Celsius. Let's talk about the heat. Let's talk about the heat capacity now. The heat capacity is the amount of energy required to increase the temperature of an object by 1 degree Celsius. Units are joules per degree Celsius. Here we are missing the gram, if you can see that very clearly. It is dependent on the mass though, and is also the intrinsic property of an object. So it also depends upon the object, how it is made up of, what are the properties of that object. Water has a high heat specific heat capacity, and whereas the metals have a lower heat capacity. Like let me take you to the slide back there, where we were talking about the water and the mercury. As you can see very clearly, water is 4.18 and mercury being 1.14. Water is a very good example, and I keep on going back to water because of the hydrogen bonding. The water has a high heat capacity. So that means 1 kg of water will take more energy to heat up than 1 kg of iron, though they are both the same amount, but they're different substances. So they will have a different heat capacity value and different specific heat value also. So metals have lower heat capacity, so it will take longer for them, more time for them to heat up as compared to water. Here, in this picture, I'm showing you a nuclear reactor and the different bodies, the basically the steam converters, which are next to the nuclear reactors. If you buy, they are next to the nuclear reactor because the nuclear reactor produces lots and lots of vast amount of energy, and they are situated next to the water body because we need water for the extra energy to get absorbed and converted into steam. So this, because water has a high heat capacity, it is acting as a very good coolant. So if your motherboard is your computer chip, your motherboard is getting really rigged, and you will use water to absorb the extra heat rather than the metal, because water being effective coolant because of the high heat capacity as it is used next to the nuclear reactor. So heat capacity equation is Q, which is the heat, is equal to m Cp delta T, and is dependent on the mass, the specific heat, and the change in temperature. I already talked to you about Q is the heat, which is measured in joules. Q is the delta H. It can both the Q delta H can be interchangeable with each other. Mass should be done in the grams. So if it is in kilogram, you have to convert it into gram. And remember, 1 kilogram is equal to 1,000 grams. Specific heat is the CP, which is specific to the substance, joules per gram degree Celsius. And delta T is the change in temperature, delta TF minus TI, the F being the final, and I being the initial. We'll do the calculations the next week on this. So let's look at the types of the heat transfer now. And this is a lesson from your middle school chemistry or science. So there are three types of heat transfers: conduction, radiation, and convection. Conduction is a transfer of heat through direct contact between the objects. As you can see, the ground and the air, then the direct contact and heat is getting transferred. Radiation is the transfer of heat as electromagnetic waves through a vacuum or a matter. As you can see, the sun is giving us heat and is transferred to the water and the land by radiation process. And convection is a transfer of heat through the movement of the fluid matter. As you can see, the warm air is rising up and the cold air will be coming down. So conduction occurs through the direct contact. As you can see here, this is the iron rod being heated on a candle. So what is going to happen is the candle is going to give us the heat, the source of the heat. It will raise the temperature. As it will raise the temperature, corresponding to the average kinetic energy or moving energy of an object. So all the particles of this steel rod, the molecules, they get heated up. And as they get heated up, the kinetic energy goes up. When the kinetic energy goes up, the motion goes up. And as a result, when the particles bump into each other, the warmer particles transfer some of the kinetic energy to the neighboring colder particles, and this keeps on going. The transfer of energy keeps on happening and happening, and ultimately the heat gets transferred to your cold hand, and your whole hand can get burned because of the conduction process. Once the thermal equilibrium is reached and particles will roughly have the same amount of kinetic energy, the heat flow will stop. Radiation. Electromagnetic waves can travel through matter and space. Remember the electromagnetic spectrum that we did? All the ultraviolet radiation, the IR, the spectrum, the UV radiation. And when objects absorb radiation, it is transformed into heat. Microwave produces electromagnetic waves, and they are absorbed by a food, causing the particles to increase vibration. So what happens when you put your food in the microwave electromagnetic radiations they come out, and they are basically increasing the kinetic energy of the particles of your food. As a result, what happens? They are the kinetic energy, the motion goes up, the heat temperature goes up, and of the air, and also of the food, and the food gets heated. Nuclear radiation in the sun produces solar radiations. So all in the sun, there are a number of nuclear reactions that are happening, and the sun produces this solar radiation, which comes to the earth. The solar radiation travels through outer space and is absorbed by the Earth. By the way, most of it is by the ocean. 71% of the Earth is covered by the ocean, and much of the solar radiation is absorbed by this ocean. Thank God that we have oceans. Otherwise, the life would have been impossible for us to, or would have not been. We would have not been able to live on the planet Earth because solar radiation is too much. If there was no water of it, no water object. So, because of these larger bodies which absorb the extra amount of the solar radiation, the light, the temperature of the Earth is livable for us. So, life is not possible in Mercury or Pluto. Number one is because of the distance, and number two is because of the lack of the ocean bodies which can absorb the extra solar radiation in the case of Mercury and Venus. Convection. Now, when the matter with particles that can move, for example, liquid and gases are heated, particles move more vigorously, sliding past each other and further apart. Now, as they are moving, as if we go back to the kinetic energy is going up. They're moving faster and faster and faster. When the faster they're moving, their mass is the same, but the space they're moving apart from each other. They're moving further apart. As a result, the volume goes up. What happens is, as the temperature goes up, the mass is the same, and density being mass over volume, the volume being go up, the density goes down. So what happens when this density goes down is results in the convection current. The warmer, less dense fluid rises to the top, and the cooler, denser fluid sink to the bottom. As you can see here in the water being boiled on the Bunsen burner. Now this Bunsen burner or the stove top is giving you a lot of heat. So this water gets heated up. As a result, the temperature goes up and um, temperature goes up, density goes down. So the warmer water will go up and the colder water in turn is going to come down. As a result, the convection currents will be created. And this convection current will even out all the heat in the water and will bring ultimately the water to the same temperature. Same thing happens in the movement of the tectonic plates. These convection currents are responsible for a lot of tectonic movements on the Earth crust. The inner core of the Earth gets warm, and this mantle is warm here. The outer crust is cold. So the mantle, the high temperature mantle, density less, tries to go at the top, the crust, and the cold crust tries to come sink at the bottom. Remember, the hot air always goes up, warmer air goes up, and the colder air always goes down. This is responsible for all the tectonic movements, the earthquakes, and as is also responsible for this same phenomenon is responsible for the ocean currents because all the Earth's surface doesn't get heated up in the same way. So wherever the ocean gets heated up a lot, it creates the warmer currents, and they always move to the colder, to the top, to the less as they're less dense, they will move the warmer water, and the colder currents are going to come down to the south, creating the ocean currents. This is responsible for the hurricanes and tsunamis, and same thing is the wind. The warmer wind going up, and the colder wind density more, colder wind density more going down, creating tsunamis and creating hurricanes. So we are done with the concepts. Now the two assignments are due by Sunday, that is by 4:26, 11:59 p.m. One is the thermochemistry practice problems. I will click on that so they can look at it. This guy is for completion for 10 points. Look at this guy. There you can see. So please answer. You can go back and review this form again and again until you get the right answer. You can go back and review my video. You can go back and review the slides which I'm going to attach to you, attach to the presentation today. And the second one is the thermo exit card, which is will be good for accuracy. Which is both these assignments are due on Sunday, 26th at 11:59 p.m. So this exit card will be graded for accuracy, and but you can go and keep on reviewing your answers and keep on correcting your answers till you get them right or till until Sunday. So basically, after whatever there are several reassessment that have opportunity that I'm allowing you to do, not only one or two. So you can keep on assessing depending upon the score that you're targeting, but whatever score that I get on Sunday, that will be your final score. There'll be a supplemental activities which will not be graded, which I'm adding to enrich your learning. Look at this worksheet that I've added to you can which you can go and review, do in your Google Docs, share it with your friends, and I'll be attaching the key also that you can review your definitions, your terms. There are simulations that I've added here, which you can go and play and have a hands-on activities to enhance your learning. And the last slide that I have is the additional resources, which are the thermochemistry notes, the CET K12 reading, conduction, convection, radiation, and the Khan Academy on the heat and temperature, which is always a very good resource for you to enhance your learning like a postman, Mr. Anderson. Please feel free to contact me, email me, let me know if you have any questions or concerns. This will be your first assignment for the first week of MP4. There will be two assignments, the overall like one completion grade and one quiz grade that will go. And let me know if you want me to have a Zoom session. The office hours you already know. So shoot me an email if you want an office session. If you are confused with any of your assignment, I'll definitely invite you on the Zoom. Thank you. Enjoy and the rest of your week and good luck.